In this lecture, we will study about solubility of solid compounds as well as gaseous compound, and we will also study Henry's law in detail. So first of all, what is solubility? Solubility of a solute compound in solvent at a particular temperature. Solubility means the dissolution of solute in solvent at a particular temperature is known as its solubility. Solubility of solid, we will understand first. Solubility of solid compound. First we will study the rule of nature, that is, like dissolves like. It means polar compounds dissolves in polar solvent and non-polar solute or say compounds dissolves in non-polar solvent. So once more we will revise. Solubility is the amount of solute that dissolved in solvent at a particular temperature. That is the solubility of that compound. Now we are going to understand like dissolves like. Means polar compounds dissolves in polar and non-polar compound dissolves in non-polar solvent. Take example of sodium chloride. Sodium chloride. It is ionic compound that can be dissolved in water in maximum amount, and we can form a solution by mixing sodium chloride in water. On the other hand, if we consider about naphthalene, then naphthalene cannot be dissolved in water. No solution can be formed because here naphthalene is non-polar compound and water is a polar compound. That is why we are unable to dissolve naphthalene in water. Now, another example we can take for the solubility is sugar. Sugar plus water also forms solution. But if we compare solubility of sugar with sodium chloride, then sodium chloride is more soluble in water compared to sugar. Now we will discuss solubility of solid solute. Solubility of solid solute depends on which factors? First factor is nature. Nature of solute. Before we study this, we will try to understand few terms related to solubility. When a solute is dissolved in solvent at a particular temperature, few solute molecules start dissolving in the solvent. The process is known as dissolution. But time will come when solute particles does not dissolve and they will collide with other solid particles of solute and the process will start, that is said to be crystallization. At the time when dissolution and crystallization becomes of equal rate, we can say no more solute will dissolve and we will get saturated solution. Saturated solution. We are unable to dissolve more amount of solute when the solution becomes saturated. On the other hand, if we consider non-saturated solution, then at particular temperature, more and more amount of solute can be dissolved if we consider the case of non-saturated solution or unsaturated solution. We can write unsaturated solution in place of non-saturated solution. That is, we can write unsaturated solution. Now we will discuss solubility of solid solute. First we will discuss nature of solute. Nature of solute. If we have a compound like KNO3, potassium nitrate, when potassium nitrate is dissolved in water, potassium nitrate, when it is dissolved in water, we can get maximum dissolution of potassium nitrate in water. On the other hand, if we have LiNO3, lithium nitrate, plus H2, if temperature increases, we are unable to dissolve more amount of lithium nitrate. On the other hand, if we have potassium nitrate, then we can increase the solubility of potassium nitrate in water by increasing the temperature. So, nature of solute. Now we will discuss effect of temperature. Effect of temperature. Solute plus solvent is equal to solution plus say heat is liberated. So in the case when solute and solvent mixes and solution is formed plus heat is liberated, in this type of solution, if temperature is increased, then solubility will decrease, because according to Le-Chatelier principle, in this equation we can see heat at the right hand side. So if temperature is increased, then back reaction will take place, and that is why for exothermic reactions temperature increase is not favorable. Same way we can take the example of say solute plus solvent is equal to solution, but here heat is supplied, means this is endothermic reaction. So when there is endothermic reaction, then supply of heat, that is increase in temperature, will be favorable for forward reaction, and we can increase the solubility of that solid compound. Now we will discuss pressure effect on solubility of solid compound. Effect of pressure. Since case of solute is related, the effect of pressure, if we increase pressure, there is no solubility increases for the case of solid solute. Now we are going to discuss solubility of gas. Solubility of gas compounds. First we will discuss nature of the gas. Take example of oxygen. Oxygen is dissolved in water up to some extent. Oxygen is dissolved in water up to some extent. On the other hand, if we have hydrogen chloride gas, then hydrogen chloride gas can be dissolved in water up to maximum level or maximum extent. That is why nature of gas is important for the solubility. Now we will discuss effect of pressure. Effect of pressure on solubility of gas. First of all, before we study the effect of pressure on solubility of gas, we will consider these two cases. In the first case, we have solution particles at the bottom and gas particles in the upper region of the vessel, and pressure P1 is exerted on the vessel. On the other hand, in the second vessel, bottom region is of solution and upper region is of gaseous phase. But by using piston, pressure is increased. Pressure is increased. So because of pressure is increased, we can see the amount of gas that is dissolved is more compared to first case. In the first case, since pressure was less, the amount of gas dissolved was less in solution, but on increasing the pressure, we get the more amount of gas that can be dissolved in solvent. Now, we will discuss temperature effect on solubility of gas. Effect of temperature on solubility of gas. Gas solute plus liquid solvent is equal to solution plus heat. So according to Le-Chatelier principle, if we have gas solute and a liquid solvent and a solution is made, but we can see that heat is liberated in this case. That is why for this case, if temperature is increased, then the solubility of gaseous solute in a liquid solvent decreases. Now we will study Henry's law. Henry was the first to give quantitative idea of solubility of gaseous solute. Henry's law. Once more, Henry was the first who gave the quantitative idea of pressure of a gas in liquid solvent. According to him, partial pressure of a gas, say P, is directly proportional to mole fraction of a gas. Once more, according to Henry's law, partial pressure of a gas, say P, is directly proportional to mole fraction of a gas. Contemporary Dalton also included that if we think about the solubility of a gas, solubility of a gas is a function of its partial pressure. Once more, we will understand. According to Henry's law, partial pressure of a gas, say P is directly proportional to its mole fraction, that is mole fraction of a gas. And contemporary Dalton also concluded that independently that solubility of a gas is function of its partial pressure. Now if we write mathematical form of Henry's law, then we can write P proportional X, and from that we get P is equal to KH into X. This is the mathematical form of Henry's law. P is equal to KH into X. Here P is equal to partial pressure of that particular gas, partial pressure of gas. Second, KH is Henry's constant, and X is equal to mole fraction of a gas. Now, if we draw the graph of partial pressure and mole fraction, then the graph will be straight line, as see on the x-axis we have taken mole fraction of HCl gas dissolved in cyclohexane, and on the y-axis vapor pressure in torr unit is taken. Once more, on the x-axis mole fraction of hydrochloric acid is taken, which was made in cyclohexane solvent, and on the y-axis we have vapor pressure in torr. When the graph is drawn, the graph is a straight line like this, and if you find out the slope of the graph will be equal to KH. Slope of the graph will be equal to KH because P is equal to KH into X, so slope is equal to KH. Now some more facts we will study for Henry's law. If KH value is decided experimentally for different gases but at constant temperature, then it was found to be different. So from that, what can we conclude? We can conclude T proportional KH proportional 1 upon solubility. So two facts we can derive from this equation, T proportional KH proportional 1 upon solubility. First is, more the temperature, more will be the value of KH. More will be the value of KH. But solubility is less. Once more the temperature, more will be the KH value, but solubility of that particular gas will be less. Second, we can say less the temperature, less will be KH value and more will be solubility. These two facts can be derived by using this formula T proportional KH proportional 1 upon solubility. Now we will study the usefulness of Henry's law. First, usefulness of Henry's law, or we can say application. Application of Henry's law. First, we can increase the amount of carbon dioxide in soft drinks. To increase the amount of carbon dioxide in soft drinks, we can utilize Henry's law. Second, for scuba divers, generally they are suffering from the medical condition is said bends. To overcome with the condition like bends, medical term bends, for the scuba divers, we can prepare the gas solution in such a way that we can overcome with the problem bends. That solution of gas is a mixture of three gases: helium, nitrogen, oxygen. And once more I revise, the gaseous mixture is helium 11.7%, nitrogen 56.2% and oxygen 32.1%. One more thing, that is the mountaineers always observe, that is say anoxia, in which thinking capacity decreases. So for these purposes, we can utilize Henry's law. Now we will study few numericals based on Henry's law. See the first case. Nitrogen gas is bubbled through water at 293 Kelvin. What we have to find out? We have to find out how many millimoles of nitrogen gas is dissolved in 1 liter of water. Two things are given to us, that is P nitrogen, that is partial pressure of nitrogen is provided to us 0.987 bar, and KH value for nitrogen gas is also provided, that is 76.48 kilobar. So how to solve sum number 1? First of all, as I told you, that P is equal to KH into X. Since we have nitrogen gas, so we will write P nitrogen is equal to KH nitrogen into X nitrogen. What are available? Which values are available? P nitrogen is available 0.987 bar. Down to that we will take value of KH of nitrogen 76.48, but it should be multiplied by 1000 because the value which is given to us is kilobar. So this unit is of bar, so this must be converted into bar. So we will get the value for X and 2, that is mole fraction of nitrogen we will get. Now in the second step, by using the formula of mole fraction, we will find again the mole fraction of nitrogen. How? Let us see. We are given 1 liter of water. 1 liter of water. So because of 1 liter we can say 1000 ml or 1000 gram, 1000 ml or 1000 gram of water. So by writing mole fraction of nitrogen is equal to moles of nitrogen divided by moles of nitrogen plus moles of water. We will get moles of nitrogen. Here moles of nitrogen plus 55.55. Why 55.55? Because when 1000 gram is divided by 18 gram molecular mass of water, we will get 55.55. But as N2 is smaller than 55.55, in the next term, we will neglect moles of N2, that is moles of nitrogen, in the denominator. So we will get N2 upon 55.55. Say number 2, say number 1 to this answer. Now we can see this is also mole fraction of nitrogen. Here also it is mole fraction of nitrogen. So on comparing these two, we will get N2 just by multiplying this answer with 55.55 means 0.987 divided by 76.48 into 1000 into 55.55. So we will get the moles of nitrogen, and from that we can also get millimoles also. Now how to solve the second sum, which is also based on Henry's law. Calculate the quantity of CO2 in 500 ml of soda water when packed under 2.5 atm pressure, provided KHCO2 is equal to 1.67 into 10 raised to 8 Pascal. So according to answer to second number question, answer to first step, according to Henry's law, again we can say P is equal to KH into X. The gas we have is CO2, that is why PCO2 is equal to KHCO2 into XCO2. From this formula, we will get XCO2, that is mole fraction of carbon dioxide, partial pressure of carbon dioxide divided by KH value for CO2. PCO2 is given 2.5 atm, but KH value is in Pascal. Convert this atm by multiplying 1.013 into 10 raised to 5. So that will be the value in Pascal. Now divided by 1.67 into 10 raised to 8. Say equation number 1. That is XCO2, mole fraction of CO2. Now in the second phase, we have 500 ml of water, that is 500 gram of water. So moles of water, we will get 500 divided by 18 gram, nearly 27. So in the third step, what we need to do, first of all we will find mole fraction of CO2 gas. Mole fraction of CO2 gas, that is moles of CO2 divided, or simply we write NCO2 plus nearly 27.27, or say nearly 500 divided by 18, whatever the answer is, nearly it must be 27. Now for the next step, we can say NCO2 smaller 500 by 18. That is why we will be able to neglect this NCO2 from the denominator. So mole fraction of CO2 will be NCO2 upon 500 by 18. Number 2. From number 1, we have mole fraction of CO2. In second equation also, we have mole fraction of CO2. On comparison of these two equations, we will be able to get the moles of carbon dioxide, and just by multiplying its molar mass, we will get the amount or say quantity.